In this video lecture, we're going to be talking about evaluation order in functional languages. And what that's going to come down to is whether we do eager evaluation of function arguments, that is, we evaluate all the arguments before calling a function, or whether we use what we would call lazy evaluation, where we defer evaluating arguments until we absolutely need to have the value of an argument. If you're looking for good notes for this lecture, you can find them in section 6.6 of the Scott text and also in my notes under other functional issues. So in the introduction, I used the words eager evaluation and lazy evaluation. The book uses the terms applicative order for eager evaluation and normal order for lazy evaluation. Applicative order is what is used in most imperative languages. They evaluate all the arguments before invoking a function. So for example, if I were to have a function call such as, say, add, and let's say I had a function call 3, 6, and another one, say, cosine 0.05, then the function calls for f and cos would be made before I ever called the add function. Contrast, normal order does not evaluate an argument until it's absolutely needed. So in this case, we would not evaluate either the function f or the value or the cosine function until we actually use those arguments in add. And normal order can sometimes be faster because it may avoid unnecessary evaluations if an expression is never used. For example, in this add function, if we never use the cosine argument, maybe we have an if then else that says if something, then return the value computed by f, else return the value computed by cos, then clearly one of the two arguments will not be necessary in each invocation. Therefore, it would be faster to use normal order evaluation. Now, we'll see in a moment why it's often faster if we use applicative order. And it basically comes down to the fact that if you don't evaluate an argument until you absolutely need it, and you need it in multiple places in your program, you will end up evaluating it multiple times. Again, we'll see that in a moment. To illustrate evaluation order and also why we may want to have normal order or lazy evaluation, take a look at the expression in front of you. We are saying that we're going to perform a division of x by y as long as y is not equal to 0. If we do applicative order evaluation, we will evaluate both branches of this and, or both expressions of this and if y is 0, then this second expression divided x by y is going to yield a division by 0 exception. This is something we don't want to happen, and in fact we're trying to guard against it by having this not y equals 0 expression. By contrast, normal order evaluation is going to first evaluate this left-hand expression not equal y 0, and if y happens to be 0, the and will be false, and we will come out of the and without ever evaluating the right-hand side argument. You also see this same behavior in the conditional and conditional or used in C, C++, and Java, and I'm sure that you have used it to your benefit before, where you've made sure that the left-hand expression has to be true before you go ahead and evaluate the right-hand side expression. So this is an example that shows why normal order evaluation can be advantageous. Now let's look at why it could be slow. Here we have a lambda function that's simply returning 2 times x. And yes, I could have written it as times 2x, but instead I wrote it this way as plus xx. And I am passing in the argument times 3, 4. And I've shown down here what the evaluation looks like if I use applicative order or with normal order. So with applicative order, I start out and I immediately evaluate this expression times 3, 4. And so double gets called with the evaluated value, which is 12. And so when we get down to evaluating plus xx, it's plus 12, 12, and that gives us 24. That's pretty much what you would expect. Let's now look at normal order. Again, we start with times 3, 4, but because we don't evaluate an argument till we actually need it, it is substituted twice down here for x. It's kind of almost like x is a macro. It's being expanded in place. So we first need the value of this left-hand operand, so we evaluate it to get 12. And now we need the value of the right operand, so we evaluate it to getting 12, and we get 24. But you see there's one additional step here because we evaluate it times 3, 4 twice. Once here, and then once here. There are techniques that we will talk about in a moment that can alleviate this problem, that effectively cache the result of multiplying 3 by 4 and then reuse that result. That technique is called memoization. But my point here is that a naive implementation of normal order evaluation can lead to slower evaluation than applicative order. In Scheme, there's different evaluation orders for different forms. So any function defined with a lambda uses applicative order. And the special forms such as cond, if, and, or, they use normal order evaluation. And I'm sure that you've seen that that's handy. For example, in the cons, you don't especially want a something farther down the food chain to be evaluated until something higher in the food chain has been evaluated. So for example, if I say less than 0a and that's true, I really only need to evaluate this expression. And it really would be a waste of time to evaluate anything in the succeeding branches. So anything that in Lisp where it might be unnecessary to evaluate some expression because of certain logics, such as the conditionals, or in the case of and, if you know the left-hand statement is false, there's no reason to evaluate the right-hand side, it's better to use normal order, and that's what Scheme does. Another thing you need to be careful about in Scheme is you need to know that arguments are evaluated right to left, not left to right as you might expect. This should not be an issue because you're not supposed to be using side effects in your code. And as long as you're not using side effects, it doesn't matter what order the arguments are evaluated in. So to give you an example of what I mean by the arguments are evaluated right to left, I've defined two functions on this screen. So the add function is simply adding 20 to its argument, and the min function is simply returning the lesser of x and y. And you can see here that I've put a trace on add, and then I'm calling min with the arguments add 5 and add 20. And since the arguments are going to be evaluated right to left, we're going to see that add is evaluated first and add 5 is evaluated second. So this is the trace I actually got when I entered this code into Scheme. And you can see that the first thing that happens is it enters procedure add with the argument 20. And it produces a result of 40. And this symbol right there, the less than equal equal, indicates we're now exiting the procedure. So at this point, we are exiting the procedure, and it shows you the arguments so that you, if there's multiple invocations that are live, you know, or have some idea of which invocation is exiting. So we're now exiting this add 20, and it has the value 40. Next, we enter the add with arguments 5. It returns the value 25 and exits. And then you can see that the lesser of 25 and 40 is 25, thus giving the final output. We can also, once we have this notion of applicative and normal order evaluation, talk about strict versus non-strict languages. Strict languages require that all arguments be well defined so that applicative order can be used. That would mean you could not have that and that I had earlier. This is not a strict expression because if y is 0, the divided x by y is not well defined. So this would be non-strict. By contrast, a non-strict language does not require all arguments to be well defined, and it would require normal order evaluation. So as we just saw, since Scheme uses applicative order evaluation for its lambda functions, it's strict for functions, but it's not strict for its special forms. And similarly, C is strict for most of its operations except for its Boolean operators. So it has conditional and conditional or. And in those two situations, it's not strict because if it knows the outcome about after evaluating the first argument of either an and or an or, it will not evaluate the second one. Now, there are times when you might like to be able to force normal order evaluation, even though Scheme wants to use applicative evaluation. And a common example of that is so-called generator functions, where you may be generating a sequence of numbers, like say the natural numbers, the Fibonacci numbers, or maybe you're trying to generate all permutations of a list of numbers and you want to be able to access those permutations one at a time. In that case, you might like to be able to only force evaluation of a function so it returns, say, one number at a time. And in Scheme, you can do that with the delay and force constructs. The delay construct creates an expression but does not evaluate it. It's essentially a promise that this expression should be able to evaluate at some point. And then forces that an evaluation of a delayed expression. So I have here a very simple example where I have defined the expression plus a10, and I have said that it is delayed. And you can also see that I later came in and evaluated or set a to 15. So now when I force the evaluation of the expression, it gets set to 25. Delay has an interesting property, which is that once you've forced the evaluation of the expression, as I did right here with force expression, the resulting value is cached. And thereafter, no matter what you change the value of a to, if I try to reevaluate this expression by forcing the evaluation, I will get 25. And the reason is that Scheme views the delay construct as a promise that once you evaluate the expression, that you will no longer change the value of any variables in that expression. That is, it will be side effect free. So I was allowed to define a value of A after I called the delay construct. In fact, I could change the value of any variable in that delay afterwards. However, once I forced the evaluation of the expression, I promised that I freeze the values of the variables in that expression. And that is so that that Scheme can use this caching technique and avoid reevaluating the expression a second time. So to give you an example of what I mean, we're going to go to the scheme interpreter and we're going to enter what we just had. So we're going to first of all define an expression, and it's going to have the value delay plus a 10. Okay, now I haven't yet provided a value for a, so I'm allowed to say define a15, and if I force the expression, I now get 25. Now let's say I redefine a as 80. You would think that if I forced the expression, I would get 90, but it's still 25, and that's because the value was cached and its value is reused. So in effect, we made a promise that we weren't going to change the value of a. Let's do it now through an actual side effect. We actually set a to be 100, and again we'll force the expression, and it's still 25. So no change to the value. You can see that changing the value of a after the fact does not change the value of the cached expression. The value that you get from the expression is going to be whatever a's value was at the time that I forced the expression. So it does not bind up the value that a had when the expression was declared. In fact, I defined a only after the expression was declared, so you can see that it uses whatever value is in effect at the time we force the expression. Okay, let's take a look at a more useful forcing of an expression and the more common use. This example is given in the Scott text, and it is enumerating the natural numbers. Well, if we are enumerating natural numbers, that's an infinite stream, and we don't want to do that. We may just want to process them one at a time. Say we may just want the top 10 or the first 10 natural numbers. So we can define what in effect is a generating function, which is going to generate a stream of natural numbers. So you see here that I'm defining naturals to be essentially a function call with 1 as my initial natural number. And you can see that it is defining a hidden helper function next that is consing n, which is the current natural number, with a call to next, which is going to create the next natural number. And this is, if you would see, if I didn't put a delay in here, this is just a nested set of conses that's consing everything together. And furthermore, without the delay, this function would never terminate because lambda functions use applicative order evaluation, so next would just recurse infinitely. By putting the delay in here, I am forcing this argument to be lazily evaluated. And you can see then how this works given the next two definitions we have. So we're just saying head is the car, so the first element of the list, and tail is going to give us the so-called rest of the list. And you see that tail itself is a function where what we're doing is we're taking the coulter of our stream, which is going to end up being this delay function right here, and it's going to force it, which is going to force the next evaluation of next. So if we take the head of naturals, we just get 1, because if naturals was just a call to next 1, and that created a cons pair with 1 and then the delay with the call to next with next plus 1. The second one here says first take the tail of naturals. So the tail, you can see here, takes a stream, and what it does is it does a cutter, so we're getting this part of it, and it's doing a force. So it's forcing the evaluation. This really is an evaluation of next 2, which is going to create the cons pair 2, and then a delay for next 3. So when we take the tail, we are going to end up doing this particular evaluation. That's going to give us this result, and when we take the car of this result, we get 2. And finally, if we take the head of the tail, then what's going to happen? Let's trace it out. We're going to start with, again, 1, and it's const with delay of next 2. So when we call this tail right here, that's going to, this should be a 2, this should be a next. It's going to take the cutter, which is that, and force right here. It's going to force the evaluation, which is going to produce 2 dot delay next 3. And now this tail right here, again, is going to take the tail and is going to force an evaluation, thus yielding the result 3 and delay next 4. And this head now extracts the 3. So in that way, we are able to extract the elements of the natural numbers one at a time. Okay, so earlier I talked about caching the results of an expression and that speeding up lazy evaluation, and I also said that the force function caches the result of an evaluation, and the technique used is one called memoization. So when an expression is evaluated, the interpreter remembers what the function name was, or the operator name, and the arguments, and it stores it in some kind of lookup table. Thereafter, when you go to evaluate an expression, the first thing it does is does a quick lookup in the table to see whether there's already a computed value for that expression, so that function with that set of operands. And if so, it simply returns that value. Otherwise, it evaluates the expression and caches the result in the lookup table. So by doing this, we get our performance of normal order evaluation within a constant factor of applicative order evaluation. Remember, if what is happening with normal order evaluation, I could construct pathological situations where I may get an exponential number of evaluations. Think of the Fibonacci sequence and a naive implementation of the Fibonacci sequence, which we went through in an earlier presentation. You get an exponential number of evaluations if you implement it naively. However, if you actually use memoization, you can reduce that to constant time, because at most you would have to evaluate each Fibonacci number once, and then you would have it thereafter. So that's why we say it brings normal order evaluation within a constant factor of applicative order evaluation. As another example, spreadsheets use memoization. If you have the 5 equations that I have shown you here, and remember spreadsheets, the rows typically have numbers and the columns have letters. So I have 3 equations and then 2 simple cell values. And if I were to modify the value of B9, then the spreadsheet would mark B10 and A10 is out of date, while leaving C10 showing up to date, basically caching its value. So if I now ask for the value of C10, it would simply return the cache value. Whereas if I ask for either the value of A10 or B10, it sees those values are out of date and it would bring them up to date by evaluating the equations. So memoization is a technique that's actually widely used to speed up the performance of spreadsheets and functional languages as well. Just remember, spreadsheets are a form of functional programming. Finally, memoization may not work properly in the presence of side effects. Here's an example. We have define x to be 5 and y to be 10, and then we basically say z is x times y, so z becomes 50. Now, if we memoize this expression, we will have that 5 times 10 is 50. And we're assuming that x doesn't change. In fact, we don't memoize 5 and 10. We memoize x and y. And therefore, this set is going to mess us up, because when we come down here, we will simply say, oh, this matches this in the lookup table, and we'll set a to be 50, which, as you can see, is not correct because x is changed to 2, and therefore the actual result should be 20. So memoization depends critically on there being no side effects. Fortunately, functional languages discourage you from creating side effects, and therefore memoization works well in a functional language environment.